Hello, my name is Rachel Moan from Winthrop University, and I'll be presenting our work on the aggregation and localization of simple robots in curved environments. This is joint work with Victor Baez and Aaron Becker at the University of Houston and Jason O'Kane at the University of South Carolina. Our paper considers algorithms for localization and aggregation of simple robots. Our main contribution is a localization algorithm for extremely simple robots contained within curved environments. At a small scale, global active localization and aggregation share the same essential structure, and they can be categorized as the same task. In both cases, we begin with a collection of candidate locations and must select actions to drive the robot or robots from those initial locations to a single destination. As a result, our algorithm is suitable for either a single mobile robot equipped with a contact sensor or a swarm of micro robots, all responding to the same global control signal. For simplicity, in this talk, we'll describe our work in terms of localization. We are broadly interested in medical applications of delivering particles to a goal location or removing particles from a region. Examples include delivering chemotherapy to tumors, MRI contrast agents to a desired organ, or clearing infection from the lungs. Our algorithm may be particularly suitable for magnetically controlled micro and nano robots, because magnetic fields easily penetrate tissue, but they simultaneously affect every magnetized object in the region. Our work was motivated by some of the limitations of prior solutions to the localization problem. Typical localization algorithms are designed for robots that are large-scale and complex, so that they can be equipped with several information-rich sensors or cameras in order to navigate their environment. For example, recent results for the localization of the Aqua 2 underwater robot rely on stereo vision combined with inertial and depth sensors. These kinds of methods would not be suitable for the applications we are interested in. Some prior theoretical work has led to localization algorithms for extremely simple robots. Unfortunately, those results are limited by an assumption that the environment is strictly polygonal. Additionally, their technique depends on the assumption that the robot stops moving immediately when it comes in contact with the environment and does not account for any sliding behavior. We address these limitations by considering the localization problem for robots with extremely limited sensing abilities contained within curved environments, as well as different motion models which allow for some sliding behavior. We consider a robot moving in a known planar environment. The robots in the applications we are targeting are expected to be controlled by potentially imprecise external forces. Therefore, we consider a model in which we can direct the robot to move in a given direction, but cannot control nor sense the extent of that movement. Based on the friction between the robot body and the environment, we consider two distinct motion models, which we refer to as the sticky model and the slipping model. In the sticky model, the robot moves in the given direction until it encounters the boundary and then stops at that point. This model matches the earlier work of O'Kane and Laval and is suitable in cases where there is significant friction between the robot and the environment boundary. In the slipping model, the robot moves in the given direction until it reaches a local maximum in that direction, possibly sliding or jumping along the boundary. This model may be more useful in practice, especially when it comes to biomedical applications, where friction tends to play a less dominant role. The robot moves within an environment modeled as a closed composite cubic Bezier curve that is constrained to be continuous and differentiable. As you may know, Bezier curves are a common tool for describing nonlinear curves used heavily in many domains. Each segment of the environment boundary is a cubic curve defined by this parametric equation. The shape of the segment is determined by 4 control points, denoted by p's in the equation. The inputs are an environment, a finite list of candidate locations, and a specified motion model, either sticky or slipping. The algorithm outputs a sequence of moves that sends all of the candidate points to one final destination. Our algorithm arbitrarily selects 2 points at locations P and Q and generates a sequence of motions to merge P and Q. The algorithm applies these motions to all of the points, including P and Q, using the specified motion model. By iterating this process, the algorithm sends all of the candidate points to the same final destination. When all of the points have been merged with each other, the robot has been localized. The question still remains, however, how do we determine the direction to move in? After selecting the 2 points P and Q, the algorithm must choose a sequence of motion directions that will combine them. There are 2 distinct cases. The first case, and the simpler case, occurs when the line segment connecting the 2 points is completely contained within the environment. In other words, the 2 points can see each other. In this case, we use the vector between the 2 points as the direction. This guarantees that P and Q will arrive at the same location. In the general case, the line segment connecting P and Q is not contained completely within the environment, meaning that the 2 points cannot see each other. In this case, P moves in a direction tangent to the boundary at point Z. This action will bring the 2 points closer to each other. This overall process is repeated until P and Q are merged, and then 2 new points are selected. To test our algorithm, we ran several simulations on different environments with varying numbers of initial points, both for the slipping model and the sticky model. Our algorithm was successful in generating plans that localized the robot. These videos demonstrate the process of selecting 2 points and moving in directions that send them to the same location, then selecting a new pair of points and repeating the process. As you can see, as more moves are executed, the number of points decreases until there is only 1 remaining possible location. To evaluate the success of our algorithm quantitatively, we measured the average distance between the points after each action was executed. In this plot, the horizontal axis shows the passage of time, and the vertical axis shows the average distance between the points. Lower values on the vertical axis indicate better localization performance. When the average distance reaches 0, the robot has been localized. As a baseline for comparison, we also executed plans of random actions. Our sequence of moves was successful, and it offers significant improvement to the simple random plan. This plot shows the results for the sticky motion model in the environment shown on the right. This plot shows the results for a similar series of simulations conducted with the slipping motion model. As you can see, the proposed algorithm localizes the robot more rapidly than the plan with random movements. We also implemented a physical proof of concept of this approach. The environment boundaries were laser cut from acrylic sheets, and the points are small glass beads. The acrylic boundary was placed on a tabletop, covered with a bucket, and translated by a UR3 robot arm in the directions determined by our algorithm. The beads move relative to the boundary, not to an external fixed point, which replicates the movements of the points in the simulation. Inside the bucket, we mounted several lights as well as a camera, which allowed us to record the movements of the beads in the acrylic boundary. This video shows an execution of a plan generated by our algorithm under the sticky motion model. To replicate the sticking model, the walls of the boundary were covered with a thin layer of dual-lock reclosable fastener strips, which causes the glass beads to stick when they come in contact with the boundary and prevents them from sliding. As you can see, the observed motions reasonably match the algorithm's predictions, and the robot is localized at the end. We also conducted tests of the slipping model utilizing a similar apparatus. We found that the bare laser-cut acrylic walls replicated the slipping model with reasonable accuracy. Again, the observed motions reasonably match the algorithm's predictions, and the robot is localized at the end. In summary, we presented an algorithm suitable for localizing and aggregating extremely simple robots contained within a curved environment. In the future, we plan to explore the optimization of choosing which 2 points to aggregate, which could minimize the plan's execution time. Additionally, we could explore different motion models between the 2 extremes that we considered here. Thank you.